Hello and welcome to the Sound and Waves unit. Before we begin, I have this amazing announcement from this amazing YouTuber. So without further ado, let's get started.
So what is sound? Well, sound is the movement of air particles through space. Do you hear me right now?
Why, yes, I do.
Sound is transmitted by a special type of wave known as a longitudinal wave. You can see that the particles move in the same direction as the sound interference. This is completely different than a transverse wave, where the energy source and the direction of energy travel are 90 degrees to each other. And if you take away the molecules that transmit sound, well, you won't be able to hear sound anymore. Like that. So sound requires a medium in order for that energy to be transmitted. So what I have here is a classic doorbell demonstration. You can hear the doorbell right now because as the hammer is hitting against the bell, it's causing the air molecules to vibrate, eventually reaching the microphone. You can still hear the doorbell right now, however it's a lot quieter because now the sound has to vibrate through the jar before reaching my microphone. Now I'm going to remove the air from the jar. Let's hear what happens after this. Without the air, you can't hear the bell anymore. There's no more material to cause the vibrations to eventually reach my microphone. If you look closely, it's still hammering away at the bell. In fact, if you want to see it in action, I can just vibrate the jar itself. So if we want to hear the bell again, I need to restore the air back into the jar. There you have it. By the end of the late 19th century, they finally figured out how to record audio onto an object. What I have here is a record. If you look closely at the record, you can see that there are grooves, and these grooves cause a needle to vibrate up and down, up and down. And if you amplify it, you can actually hear sound with it. Now, please don't try this with your favorite record. You'll notice it's very quiet. Can't hear anything at all. What I need to do is I need to amplify the sound and cause lots of air to move back and forth. And one way of accomplishing that is by making a cone out of a piece of paper. If you attach the needle to the end of the cone behaves as a natural amplifier, causing larger amounts of air to move back and forth. Of course, with conventional record players, we don't use a cone anymore. Instead, there's a little needle at the top of the record player, which when it senses the vibrations, it sends a signal to an amplifier, which then amplifies the signal to a speaker. Of course, the next question is, how in the world does a speaker work in the first place? Time for another episode. There are three components.
We'll save that adventure for another day. For now, let's just start off by the introduction towards this new unit. We're talking about mechanical waves, and sound is an excellent example of a mechanical wave. Right.
Listen,
Yes.
Ashim, the chat's not available.
The what's not available?
Chat, like we can't type anything in the chat.
Huh, that is very weird. Anyways, I'm just going to let this run right now while I try to diagnose the problem. And if you're wondering, how do you copy this down? Let me just give the instructions first. You probably want to just draw this as a sinusoidal wave. It'll be easier to draw just like this. And then you emphasize the extremes. You have your crest, you have your trough, and the midway point between the crest and the trough, if you recall from back in grade 10, is known as the rest. All right, so you can jot that down in your notes, and I'm going to diagnose and see what's going on here. I think you're able to type in comments now. There you go. Thank you. Yep, make sure you like, subscribe, and all that fun stuff. Oh, you should watch the whole video to see how many times you get rolled on it. Can you believe I actually have the record? I actually own that record. It's awesome. Okay, so yeah, have that jotted in your notes. This is a transverse wave. And just like in the video, transverse wave is one where the energy interference and the direction of energy transfer are 90 degrees to each other, or perpendicular, or even better yet, we'll use the nerdy term orthogonal. Remember that orthogonal means that these two dimensions are 90 degrees to each other in three-dimensional space, right? So that is the nature of a transverse wave. The interference is perpendicular to the direction of energy transfer. Compare that with a longitudinal wave, and that's the next type of wave that we're going to discuss. Oh, this cool video right here. All right, I didn't do this, but yeah, if you ever had a chance to go to the gym, probably you played with these thunder whips over here. That's an excellent example of a transverse wave. Look how glorious that is. All right, you can see that the disturbance is going up and down, but the energy transfer is traveling across.
Do this workout for 20 to 25 seconds.
Oh, there was an audio with that. I forgot about that. Okay, so we can compare and contrast that with a longitudinal wave. And a longitudinal wave is one where the energy disturbance and the direction of energy travel are parallel to each other. And if you're wondering how in the world are they going to jot this picture down, most people will draw this as a static image. All right, so then they'll freeze frame like that. Where's the freeze frame? Ah, there you go. No, that didn't work. Anyways, you just draw a bunch of dots where there are the gas particles that are really close to each other, and then a gap in space, and then a bunch of them together, void in space, so on and so forth. And yes, there's a name for these regions. The regions where all the gas particles are all squished with each other, it's known as a region of compression. And the regions where there's a void of gas particles, just make sure you spell this out correctly, it's known as a rarefaction. Okay, some people accidentally write it down as rarefaction. No, it's rarefaction. You know, there are no fractions here. All right, don't be fooled by the optical illusion over here. Stare at any given dot on the animation. Okay, just pick one dot and just keep on staring away at it. You'll notice that dot, it doesn't leave its spot. All right, it'll jiggle back and forth or up and down, but in both of these animations, none of the particles leave their region. They all stay in the same region. It's the energy that travels across. So yes, you are seeing energy propagate across. That is true. Okay, and that is the nature of all types of waves. Okay, so with all waves, the particles remain relatively in the same location, and it is the energy that propagates to the far end. With regards to sound, sound is transmitted in the form of longitudinal waves. However, often, if you've ever done any audio recordings, you'll notice it's recorded as a transverse wave. And if you're wondering why that's true, it has to do with what's easier to read. Because you can imagine that if you did an audio recording and had nothing but just dots on the screen, it would be very hard to figure out where to start editing. You can't tell where it's quiet and where it's loud because there's just dots everywhere. So we translate it into a way that's more recognizable by a human being. Hopefully you guys know what I'm talking about. Let me just open up one of my favorite audio editing programs. And it's called Cool Edit 2000. Yep, made in the year 1999. Still works to this day. There you go. Cool Edit 2000. Okay. So let's record Mr. Nee's voice. Hey, this is Mr. Nee's voice. How y'all doing today? And there you have it. Okay. So even though my voice is really just compressing gas particles away from my mouth, and it's just continuously moving the wavefront towards where the microphone, which is up there, as an audio recording, we always draw it as a transverse wave, like so. Okay, and the purpose of drawing as a transverse wave is so that it's easier for us to see. So oscilloscopes will record sound waves as a transverse wave as well, all right, as well as audio editing programs. So you can see the regions at top, which are the regions of compression, and all the way at the bottom are the regions of rarefaction. Okay, so that's why it's recorded the way that it is done, because it's easier to see, you know, the regions of silence and the regions of noise. Hey, this is Mr. Knee's voice. How y'all doing today? There you go. All right. And yeah, there are other ways to see sound. I can actually change this around. This is the cool thing with the software. I can take a look at a spectral analysis. So this is just a different way of seeing sound by looking at it as intensities of frequencies. So where it's very bright, that's a region where that frequency is very prominent. And hey, this is Mr. Knee's voice. How y'all doing today? All right. And by looking at the patterns in the sequence over here, this is how AI is actually able to do voice recognition, right? It's by looking at the trends in frequencies. Any other questions before we advance on? Okay, so as mentioned, waves are often drawn as a transverse wave. Now, if you weren't paying attention to the labeling of the title or how the axes are labeled, you would say that these two diagrams are exactly the same. Rarefaction
Can we just go back to the previous slide?
Sorry, your question was?
Can we quickly go back to the previous slide?
Sure. Here you go. Okay. So compression is a region where I wish I could pause the video. I think it's this button, isn't it? Yeah, that's how you pause it. Okay. So compression is a region where there is an abundance of gas particles squished together, and the rarefaction are the regions directly in between where there's a lack of gas molecules. Rarefaction. Yeah, the rarefaction. Okay, so rarefaction is a region where there's a lack of gas molecules. At the end of the day, with regards to the properties of gases, it always wants to reach an equilibrium. All right, it wants to reach a steady state where the air pressure is uniform throughout the entire room. So while I'm speaking, I'm actually creating a disturbance. I'm actually forcing gas particles to squish amongst each other. And as they expand, because they don't want to have one region higher than another region, so the regions of higher air pressure will move into the regions of lower air pressure, which is where the rarefaction is. However, in doing so, the momentum of the air molecules collide with the next adjacent air molecule, and that's how sound propagates through space. Right? It's just air molecules knocking out other air molecules until everything is at a uniform air pressure. All right? Compression is where the gas molecules are all packed close with each other. Crest, yes, is at the top of a wavefront, and a trough is at the bottom of a transverse wave. Sorry, not wavefront, a transverse wave. Again, the way how you draw this is that you probably just draw it as one clean transverse wave, as opposed to one made up of all these different molecules, just to keep the pictures nice and clean. Can I explain parallel in longitudinal waves? Again, with regards to longitudinal waves, the disturbance is going left and right, right? You can see that red bar, as I animate it again, it's going left and right. You could also see that the energy also goes left and right. So the direction of the disturbance is in the same direction as the energy as it passes through space. On the other hand, with a transverse wave, you can see that the disturbance goes up and down, but the energy, if you ride the wave like a surfer, it moves towards the right. Yes, the rarefactions are the gaps between the compressions. All right, can I advance on now? Anyone else need me to pause? Just raise their hand up. Okay, just make sure you drop it when you're done so I can advance onwards. All right, and so just like in the video, there is no sound in space, all right? Because when you're in space or when you're in a vacuum, there's no gas particles to collide with one another to propagate the energy across. So yeah, if you're out in space and you try shouting, nothing's gonna happen. You're not gonna hear any noise, okay? Okay, so the graphical interpretation of waves, Again, without showing the labels of the vertical axis and horizontal axis, these two graphs look identical, but they do have different meanings once you label them. The graph that's on the left is the same as the graph that you'd see in any audio editing program, right? Where it's showing you the intensity of the gas pressure as time goes by. So it's a measurement of amplitude over time. On the other hand, with the diagram that's on the right-hand side, it's as if you took a picture of that person playing with that wave-making machine from that YouTube video that you saw. So for a bit more terminology, again, amplitude is the intensity of the wave. What could be measured in? Well, it just depends upon what you're aiming at. All right, so that's why I'm just going to call it amplitude, because it could be measured using many different types of units. Okay. Instead, I'd rather pinpoint other key ideas. For example, with regards to a periodic wave, so a wave where the pattern repeats itself over and over and over again, the time between successive repetitions, that's known as the period. All right. Now, you could measure the period like how I've shown you graphically over here, but most of the time, we'd rather measure it from crest to crest. All right. One of the issues about measuring from rest to rest is that if you measure it between these two, you'll see that it's not that of a full period. It's only half of the numerical value. So that's why rarely we measure periods from rest to rest, right? Because you can accidentally get half the correct answer. So instead, we'll either measure it from crest to crest, or we measure it from trough to trough. And that is true whether if you're trying to measure out period or if you're trying to measure out wavelength. Okay. What is a wavelength? It's like taking that picture and placing a ruler in front of the picture. You're literally measuring out the length of the wave, and that's where it gets its name. Okay, so you're just dropping a ruler on top, and you're measuring from crest to crest. And let's say in this diagram over here, as I measured on my screen, I get the answer of 5 centimeters. So that's the wavelength on the diagram on the right. On the left, if I measure it out, I need to measure it according to the time scale, and I'll figure out how many seconds have gone by. Okay, so that's the difference between the two graphs. One is a measurement of how much time has gone by before the wave repeats itself, and the other one is a spatial diagram. So it's someone who took a picture with a ruler in the background so that you can see what the physical wavelength is. Wavelength is measured using the symbol lambda. Where is it? Right here. Okay. Lambda is used to measure wavelength. Yeah, so there was a question about noises in space. Yeah, whether if it's spaceships exploding or meteors and rocks colliding with one another. If it releases a lot of thermal energy in the form of infrared radiation, yeah, our skin can feel it, right? We can probably see even the light as well. So that will pass through a vacuum. So we can feel the warmth if we're in a spaceship and we see the brightness of it all, but we're not going to be able to hear the sound at all. The sound is always added as just an enhancement to the movie. Anyone else still need the slide before I move on to the next one? Just a raise of hands if you need a bit more time. Okay, so again, all I did over here was I just defined it. The text in blue, do you need to copy it down? If you're already comfortable with the definition, no, you don't need to copy it down. But if it's your first time seeing it and you want your notes, you're more than welcome to either jot it down or again, go into Google Classroom and just download the PowerPoint slide and just copy from there again, okay? So this is just terminology over here. Some things that don't resolve very well when I do this remotely, and that's why if you guys want to try it out, you can try it out from the comfort of your own home, is what I would normally do is I'd play this sound recording, which is a frequency sweep. I'll show you what it looks like, but it probably won't resolve very well, as anytime that I'm transmitting information through this method, through this form, often with speech, they try to compress it to get rid of background sounds. And in the process of doing that, you end up losing some of the frequencies. So it doesn't sound the way how it would if you were here with me right now. Okay, so I'll just tell you what it is. Wow, it's still on the spectral analysis, which is pretty neat. Okay, as I said, this is a cool way of just seeing what frequencies exist in the sound recording. So you'll see that I start off with very low frequencies, and that's what the vertical scale is. It's just telling you what frequencies are prominent in the recording. And as time goes by, you can see that the frequency increases. And I don't make it increase up linearly because it just takes too long to gradually ramp up. All right. So I start off with very low frequencies, and eventually I just, I think this is almost exponential, where the frequencies just double up on each other. Okay. All right. So I'm going to switch over to the regular view. All right, where again, this is a measurement of amplitude, which is the vertical dimension versus time. I don't know if you can see the text on the right-hand side. Currently, the amplitude is measured in decibels, but you can also measure the amplitude in, what is this, samples, all right? And 16-bit samples, you can record it as a percentage or normalization to a value of 1, or you can measure it relative to 100%. So that's why with amplitude, I'm just keeping it very arbitrary because it depends on how you want to measure the amplitude axis. But horizontally here, as what is listed down here, these are all the time codes. So if you measure the distance between, for example, the crest on top over here versus the crest on top over there, you can find out the corresponding frequency here. Okay. So I'm going to play this recording. I know it's not going to resolve well, but you'll notice the general pattern, right? When I start off with at lower frequencies, the period is very long. And as I increase the frequency, the period will keep on decreasing. So I'm going to start from the beginning and let the whole thing run through. Okay. I'm not sure if you guys can hear these very low frequencies. I start off at, I think, around 20 hertz, and it ramps up. Don't know if you guys heard that blip right there. I could hear it, at least from my end. Right now, it's probably around 1 kilohertz. Then it's going to grow quite quickly to 2, 4, probably around 4 kilohertz right now. It's usually as annoying as this. Right here, that's 4 kilohertz. How do you know? It gets louder to the ear, and we'll talk about the science of why that happens. All right, so it's still playing a frequency even at the end. I don't know if it's being transmitted through or not. As I said, it's just the reality of how things are recorded or are transmitted through Google Meet, all right? Google Meet already knows that this is a vocal conversation. And with most vocal conversations, you don't need to transmit frequencies beyond 4 kilohertz. So for the most part, anything above 4 kilohertz usually gets deleted in recording. And that's why if you ever talked on an old school telephone with those conversations, the reason why it sounds like this is because all the higher frequencies have been deleted. All right, so anything above 4 kilohertz is usually deleted there, mainly for efficiency. All right, if you don't really need that recording to understand somebody, then why include it in the first place? Okay. So that's what you would have noticed. There's an inverse relationship between period and frequency. So as the frequency increased, the period started to drop. You'll notice that the time between successive crests got closer and closer. Guys, let's try to keep the conversations nice and clean there. By definition, frequency is the number of occurrences of a pattern in 1 second. That's why you'll see that the formula for frequency is n over delta t. Period is the reciprocal of frequency. And that's why period is how much time it takes for one occurrence to happen. Okay, so you'll see that the values have been flipped around between period and frequency. And that's why the relationship between these two, they are a reciprocal relationship. All right, so the formula that you will be using is based upon the circumstance. Let's go through some of these examples together. N is for the number of events or number of occurrences. Okay, so let's practice through these examples over here. Example number 1A, determine the period. So we're trying to solve for t. Okay, what is t equal to? And you'll see that they've given us two measurements. All right, 33.333 turns is our number of occurrences. So that will go in the denominator. So 33.3 is the number of events. And this happens in the duration of 1 minute. One thing just to let you guys know, with regards to period and frequency, often the time reference is measured in either seconds or per second. Okay, so that's why we want to convert that minute into 60 seconds. We then take out our trusty calculator. We do 60 divided by 33.3. And 60 seconds divided by 33.3 events tells us the time between events. All right, so our period in our first case is 1.8 seconds per occurrence. All right, N is for the number of events or number of occurrences. Let's try out the next one. Okay, let's find out the period, and period is denoted with a capital T. Right. So 68 sit-ups in 57 seconds. That's a pretty good gym-going person to do that. I'm sure I will not be able to attain that. Again, period is time, which is 57 seconds, divided by the number of events. So 68 setups. 57 divided by 68 gives us 0.84. And that's our period. All right. So again, period is the number of time it takes for you to do one action, and you're assuming the action repeats itself over and over and over again. That's one of the qualities of period. Okay. Some people might be wondering, well, what makes delta T and capital T any different? I mean, for one thing, they both measure the unit of time in seconds. That is true. The difference between these two is that delta T is for a one-time event. All right. Just like in kinematics, right? Johnny is scared of a dog, so Johnny accelerates from 2 meters per second to 5 meters per second in 3 seconds, right? So it took 3 seconds, and that was it. You're not expecting Johnny to accelerate again and again and again and again, time after time after time. On the other hand, for example, with regards to this ruler, if I swing it back and forth, and as I slowly hypnotize you guys at home, you'll notice that the time it takes for this to go back and forth is pretty much the same value each and every single time. It's one of the properties of the mass that's over here and its length. Actually, it's mainly based upon its length and which planet you're doing it in. Okay, so I can change the mass of this, and the outcome, at least in this setup over here, will be identical. All right, so if it's an event that repeats itself over and over again, that's when we describe it as capital T or period. Okay, so for repeating events. An excellent example of it is here in high school. Right? I know it doesn't happen in summer school, but during regular school, what happens? You wake up, you brush your teeth, you go to school. School starts at, let's say, 8:10. And then that period lasts for 75 minutes. Then you leave for 5 minutes. You go to the next class. That next class lasts for another 75 minutes. You leave. You have another period, which could be lunch. That's 75 minutes. You leave from there. You go to your next class, which is 75. And that 75 just keeps on happening over and over and over again. That's why they call it first period, second period, third period, fourth period, and maybe even fifth period, depending on the school that you go to. All right, period means it's the amount of time that's always going to be the same quantity over and over again. All right, so repeating patterns are described using period. Fun fact, that's why the periodic table is named the way that it is. It's a pattern that just repeats itself over and over and over again. Why are there 4 formulas? It's really about what you're trying to measure that moment. Knowing that frequency is the number of events as time goes by, or the reciprocal, which is the time that goes by per event, which is your period. Lastly, period and frequency, they are inversely correlated with each other. So it's really just the reciprocal formula. Pick and choose the formula that you need to solve that particular problem. For example, if you're trying to determine the frequency of 120 oscillations, which is repetitions, in 2 seconds. Frequency, again, is equal to the number of events divided by the total time, so you can find out the amount of time per event. All right, so 120 oscillations divided by 2 seconds will give you an answer of 60. 60 of 1 over s. All right, which could also be represented by, and let me just put up some more space for this because that's getting kind of crammed up there. Yeah, let me just use this guy over here. So 120 over 2.0 seconds gives you 60 1 over s, which is also equal to 60. Well, 1 over s is the same thing as s to the power of -1, but those two nomenclatures aren't often used. Instead, we commonly use the reference of hz. Okay, so 1 over seconds has the same meaning as s to the -1, which today we'll call it a hertz, named in honor of Henrik Hertz, the scientist who was in competition with regards to Nikola Tesla and Thomas Edison in trying to transmit electricity wirelessly. However, in his experiments, he accidentally transmitted a signal. And that's why, with regards to radio and telecommunications, we measure signal transmissions in hertz in honor of Henrik Hertz, who was trying to transmit electricity wirelessly, but figured out that, hey, what I'm really doing is I'm just sending a Morse code signal through the air. Okay, the last one. Again, frequency is equal to number of events, so 40 pulses over time, but remember the time needs to be measured in hours, or sorry, in seconds. Okay, so you have to convert the hours into seconds. So you have 40 is equal to, 40 over 1.2 hours is multiplied by, for every 1 hour, there are 3,600 seconds, and that's how we can get it into per second, right? Per second is hertz. So 40 divided by 1.2 divided by 3,600, it does give you a very small value. And if you're wondering, why am I only showing 2 sig figs? If it's a final answer, it's all based upon the least certain measurement. All right. So for example, in D, 2 sig fig, 2 sig fig, that's why our final answer is 2 sig fig. And the same is true for all the other examples. Now, with regards to describing frequency for the last example of 0.0093 hertz, it's a rather small number, and usually that doesn't make any sense at all. So instead, if you need to describe a value that's very small, you probably won't measure it in frequency. You'll measure it as a period, and period is equal to 1 over frequency. So really, we're just taking the reciprocal of that answer there. So the reciprocal of, well, I better calculate it out first. 40 divided by 1.2 divided by 3,600, just so I have some extra sig fig. And then I'm going to reciprocate that. All right. So normally, if a number is that small, you'd probably just describe it as a period where it took 108 seconds for one event to occur. All right. So is there a difference between choosing frequency or period as your final answer? They're both correct. If there's one that's more correct, if you're curious about that, it's the one that which shows numbers that are larger than 0. Or sorry, larger than 1. Okay. So if values are larger than 1, you probably want to describe it using that unit. Okay. So with very low frequencies, you'll measure as a period, and with very short periods, you'll measure it as a frequency. Now, sound waves can fall into 3 extremes, right? The audible spectrum, which you can hear my voice right now, and then the inaudible parts. Most of us have already heard of the term ultrasound. Ultra meaning above the audible hearing range. But there's also sound that exists in the opposite range as well. If you take care of the color spectrum, right, good old Roy G. Viv, before the red, you have infrared, meaning before what the human can perceive. And then after blue, you have violet, and after violet, you have ultraviolet. Ultra for being above and beyond what a human being can pick up. So we use these prefixes for sound as well. So ultrasound are frequencies that are above audible hearing range. And yes, there is such thing as infrasound as well. Infrasonic waves or infrasonic frequencies are frequencies that are below the audible hearing range, which is typically below 20 hertz. This joke works better when you're with me in the classroom, where I'll just tell you that, hey, class, I'm going to make a really loud sound right now. Okay, I'm going to make a really loud sound at 3 hertz. What do? I take my hand and I just do this. You guys hear it? Now, I know that one reality is that the microphone will not pick up that lower frequency, so you're not going to hear it on your end. But you can imagine that if you're with me in the classroom and I'm doing this, you'll think I'm crazy, but I am making a sound. All right, it's just that our ears cannot pick up frequencies that low. Just like how we can't hear a dog whistle, frequencies that are that high. Other organisms can pick it up fairly easily. All right. For example, whales and elephants, they have no problems at all listening to those lower end frequencies. In fact, scientists believe that that's their form of communication to each other through long distances. I normally repeat my recording of a high sweep. So I usually start off at, I think, around 4 kilohertz, and I go up from there. And it's just to hear where the cutoff is for everyone in the classroom. So everyone's going to have a different high-end cutoff. Generically, we just stick it at 20 kilohertz, but normally as you age, your ability towards hearing higher end frequencies diminishes. All right. So, a person of my age, I definitely cannot hear a frequency of 20 kilohertz. It doesn't happen for me. These recordings are available in Google Classroom if you do want to listen to them yourself because you enjoy listening to audible pain. Anyone else still need the slide before I move on? Just a raise of hands if you need me to pause this for a sec. Okay. Just make sure you drop it once you're ready for me to move on. Yeah, so that's why on the slide, if you end up buying, headphones, in the back box, they'll tell you the response frequency. In other words, what frequencies is it able to generate? And most of the time, they'll talk about a range here because this is all human beings can hear. So there's no point in it generating a lower frequency, and there's no point in it generating an even higher frequency. Wait, so frequency determines how much sound we can hear? No, frequency is the number of events that occur in compressions and rarefactions, and our ability to hear is not uniform. You might notice that if you play the audio recording at home if you want to, for example, the 20 hertz to 20 kilohertz, at 20 hertz, you won't notice anything at all. And if you look at your speaker, if you have those big, huge speakers, you'll see it's going to wobble back and forth like crazy, but our ears can't pick it up. So it's generating a lot of sound, but our ears are not sensitive to that lower end frequency. All right, and then there is a sweet spot at around 4 kilohertz where it starts to hurt our ears. Now, trust me, in the entire audio recording, do I still have it open? Let me just try opening it up again. You'll notice that I did keep it at a fixed amplitude, the entire recording. Okay, so I kept the entire recording at probably negative 6 dB or so, just so I don't bottom out or I don't top out. Yeah, negative 6 dB. So in other words, it's going to be 4 times less than the loudest sound your speakers can make, just so I don't destroy anybody's speaker. All right. So regardless if we're talking about a very low frequency right over here, where the period is long, or a very high frequency, you'll notice that the amplitude remains the same. Yet when we get to around 4 kilohertz, so while you're listening to the recording, it suddenly gets louder and louder and louder, and then starts to hurt your ear. But after that, it's going to start to diminish afterwards. Partially has to do with the speakers you have at home. Chances are very few of you guys have speakers that are $400 a piece. Yeah, when speakers get really nice, they sell them to you individually. You don't buy them as a pair. You buy them one at a time. All right. And the science of why we perceive those middle frequencies so loudly, well, we won't learn that until about 2 classes from now, or 2 days from now. Okay, so in 2 days from now, I'll explain to you why we somehow have an elevated sensitivity to certain frequencies and why it diminishes afterwards. It has to do with something called resonance. Okay, I'll save that for a future lesson. Okay, I think that's more than enough time right now. The universal wave equation at the end of the day is V equals F lambda. Okay, so I could just tell you, yep, V is equal to F lambda. Let's just start calculating away and end the period. I could do that. But let's just talk about where this formula comes from, and then you'll have a better appreciation of how to apply it and everything. Okay, so we know that waves will pass through space, and it'll take a certain amount of time for it to pass through the space. Okay, so we measure the time it takes for a crest to get from point A to point B. We have our measurement in time, and we have a measurable distance. But that distance, we don't call it a regular distance. This is a physical distance that you can drop a ruler on top of a wave. So we don't call it distance anymore. Instead, we use the term wavelength. Okay, so delta D is equal to lambda. Now we're taking it that's kind of like the thunder ropes, where you're repeating the pattern over and over and over again. And I guess I wrote it here already as that, but yeah, T, okay, for a repeating period in time. Okay. Now, the universal wave equation is one that assumes that you're in the same medium, so that the wave will just propagate constantly at that same speed. Because once you change mediums, the speed of a wave either speeds up or slows down, something that you learned back in grade 10 science in optics, right? When you go from a less optically dense to a more optically dense medium, the speed of light will slow down, right? So the universal wave equation is assuming that you're going through that same material or the same medium. All right, and the whole formula stems from this basic one. D is equal to V delta T. We'll just replace D with lambda, because as I said, it's a physical distance for a wave to travel across. As for T, we're going to replace it with capital T because the pattern repeats itself over and over again. Another thing is that you know that T is equal to 1 over F. So this equation can be rewritten as lambda is equal to V 1 over F. And by just swapping things around, so we have F lambda is equal to V, or our last step is V equals F lambda. So that's the story of how this universal equation came to be. Will I test you that on that? No, you won't be tested on that. All right, I'm just showing you that this is how the formula is created. It's one of the nice things about physics. There's a story behind every single formula and how it's generated. Okay. And this is known as the universal wave equation because anything that behaves as a wave will follow this formula. Right now, we're covering mechanical waves, so waves that are moving on a physical string, waves through sound that you can hear. But don't forget, even light behaves as a wave, so light will use this formula. And as crazy as it sounds, because light is part of the electromagnetic spectrum, that means that anything that's electromagnetic is also a wave as well. All right, so even electricity, as it passes through space, it behaves as a wave, and it will also abide by this formula. That's why they call it a universal wave equation. But for grade 11, we're only going to be using this equation with physical objects, so waves on a string, or even waves with compressions and rarefactions in air, and that's all we'll stick to here. All right, so I'll give you guys a moment to jot down example number 2. It is a ridiculous example. It's normally done the other way around, but I just want to get an idea across, and that's why we're going through this example. Okay, so I'll give you guys a moment to jot that down. And something I haven't done yet is for you guys to type in hello. So you guys mind just typing in hello so I can quickly go through attendance right now? Much appreciated. Okay, so let's go through this calculation. All right. First off, we got to figure out what the frequency of this is. So we see that the fork, tuning fork, I forgot to bring one, so I'll just draw a picture for you. Tuning forks look like this, right? Why do they look like this? It's because they're trying to maintain a center of gravity. So when you end up striking one of the tines, the other one will actually move inwards as well to maintain that center of mass. And then when the first one moves back, the second one will move back as well. So that's why there's two tines. It's just to maintain the center of mass so that it can resonate indefinitely or almost indefinitely. All right, so you're experiencing all the compressions and rarefactions between the two tines. One mistake that most students make is that when they pick up a tuning fork, they say, oh, this is pretty cool, and they whack it against the edge of a table. Little do they know they've already detuned that tuning fork. All right, because anytime you strike that tuning fork against a sharp edge, a small piece of metal chips off, and it denatures that its natural resonant frequency. All right, it's going to throw it off, and it's going to be a new value that's not the same as what's listed on the tuning fork. So if you guys ever have an opportunity to use a tuning fork in the future, please do not actuate the tuning fork using the edge of a table. There's this piece of rubber, and it's called an actuator. All right, and its whole purpose is for you to strike the tuning fork on something soft so that the tines are able to resonate without losing any of the metal. All right, so you're supposed to strike it on something soft. And if you don't have that piece of rubber to strike it against, you can strike it against your thigh, and you'll get the idea across. Okay, when I have a chance later on, I'll dig one out because I'm sure I have one in a box somewhere, and I'll show you the right way versus the wrong way of using a tuning fork. Okay, so this tuning fork, it vibrates, so the number of occurrences is 375 times in the duration of 3 seconds. And it repeats itself over and over again so we can find out the corresponding frequency. So frequency is equal to 375 divided by 3 seconds, which will give us 125 per second. Again, instead of calling it 125 per second, because that's just hard on the eyes, instead, we'll just name it hertz, 125 space hertz. Okay. Next part is calculate the speed of the sound wave. All right. What is the speed of sound? And that's what I'm trying to allude to over here. Okay. The speed of sound is equal to the frequency of the sound times the wavelength. Frequency we just discovered, 125 hertz. And the wavelength, would you really know that the wavelength is 2.75 meters in real life? There are ways of doing it these days. There's this cool hack where you take light and then you break light, you shine light through a razor blade, and then you have that light transmit to the far end, and you have a concave mirror on the far end that which reflects it back, and you look at the interference of those two light sources with a high quality camera, and then you can see how how the sound waves propagate through space. So there are ways to do it as a hack, but normally with the naked eye, we cannot see the distances between compressions. Okay, and that's why I said this question here is unreasonable from that perspective. You'll never know that it's 2.75 meters. Instead, you'll reverse calculate and figure out that it's 2.75 meters. Okay, so what you'll really know first is the speed of sound, and that's why I've shown you this formula here, just so that we can get to, this is the approximate speed of sound in a room. So we're going to multiply 125 by 2.75 meters. Remember, you need to convert into meters. So if you accidentally got a very big value for V, it's because you didn't convert to meters, and you'll get an answer, at least on your calculator, of 343.75 meters times hertz. Remember that hertz means per second, so you're getting 344 meters per second. Okay, and that's the approximate speed of sound, somewhere in the ballpark of 350 meters per second. It really is based upon the air temperature. If you remember from the previous unit, as I mentioned, at higher temperatures, molecules jiggle a lot faster. So at higher air temperatures, when I transmit a sound wave, since the air molecules are moving faster, they'll bump far sooner into the next gas molecule. So in other words, the speed of sound increases at higher temperatures, and the speed of sound will decrease at lower temperatures. That is a trend that is true. What is a unit after 343.75? Again, I initially wrote it down as hertz times meters, or meters times hertz, because that's what I got, right? I got hertz and meters, so I wrote down meters times hertz. But again, no one writes it down as meters times hertz. We know that a hertz is equal to 1 over seconds, and that's how it turns into meters per second. You mean, when do we use seconds? No, more like seconds to the -1. All right. Remember, seconds to the -1 is equal to a hertz. Seconds is just equal to a second. Okay. Be careful with that because seconds to the negative 1 has the same meaning as 1 over seconds. All right, so if you're measuring period, you'd measure it in seconds. If you're measuring frequency, you would measure it in per second, or you would measure it in hertz. Any other questions before we move on? Okay, so the whole purpose of example number 2 is just to let you know that, yeah, the speed of sound in a room is somewhere in the ballpark of this number here, around 350 meters per second. How would you know what it is specifically? We'll cover that in a future lesson. Okay, so this just introduces us to the speed of sound. Yeah, this is the number it's at, okay, 300 something. What is the unit you wrote beside N? I don't have an N here. Oh, N. 375. Why did I wrote down N? Oh, it's just 375. Number of occurrences. No problem. I guess I'm more organized than I thought because I just looked into the distance, and on my shelf, see, I have a box of scientific fun in here. So here are some tuning forks. I do have some around. Okay. Again, the proper way of striking a tuning fork is to strike it against a soft surface. Palm of your hand works just fine. And that is a resonant frequency of this tuning fork. I know you can't hear it. That's why I'm going to bring this close to the microphone. Did you hear that? That's soothing. Okay. That is the proper frequency of this tuning fork. The problem is that students end up doing something crazy like this. Oh, tuning forks! And that's when you've wrecked it. Did you hear that high frequency pitch? The high frequency pitch is when these tuning forks are now wobbling like crazy like this while they go backwards and forwards. You're causing it to resonate at its overtones and you'll wreck it. Why did Mr. Nee wreck these? Because they've already been chipped. If you look at the edge, they're already destroyed. I do not know what frequency this is right now. So it's already GG. It's already a good game. But now you know, okay? Whenever you have a tuning fork in the future, strike it somewhere soft because you should only be hearing its fundamental frequency, not the crazy high-pierced overtone. That's when you're doing it incorrectly. Now you know. Okay, next slide. Okay, so this is one of those weird things about waves, okay? Whenever waves change from one medium to the next, crazy stuff starts to happen, okay? I'll go from the example from less to more, and then I'll move on to the example from more to less dense. So this relates to what you learned back in grade 10 in optics, right? You would have learned that from less to more, the light bends towards the normal, but a second consequence is that whenever you go from a less to more dense medium, the speed of light slows down. And this is true with regards to waves. When you go from a less dense medium to a more dense medium, the speed of that wave does decrease. There's the animation to prove it. But there's also these other weird side effects as well. Anytime you go from one medium to the next, you end up also having this weird reflection. Okay, and if you take a look at this example over here, you'll see that the wave flips upside down. It inverts and then bounces back to its source. It is a consequence whenever you change mediums. You're going to have a bit of a reflection. If you're wondering how in the world do you copy something like this down, well, you can see that the more dense medium is thicker. That's true. Okay, so in your notes, you'll have a before, and then you'll have an after. So before, you have this scenario here, and you'll draw a V with an arrow to tell the reader that this is the speed that I was traveling at before. Afterwards, you'll see that the wave inverts itself. The amplitude isn't as great, all right? But the transmitted medium, here are the things that occur. For one thing, its amplitude has decreased from the original source. You'll also notice that the wavelength has gotten shorter, and it also travels slower. So to show that in your notes, AFTER, you'll have a V that's shorter over here. Tell the reader that it's traveling slower now through the new medium. And when it reflects back, remember, you're in the same medium as the before medium. So the length of that V vector should be the same because you're traveling at the same velocity when you reflect back as you're still going through that less dense material. Okay, so the speed will be the same on the material on the left. Okay, so that's how you jot it down in your notes. Maybe I'll write it down here because I got to erase that, and then you'll have your text notes afterwards. So you have your before, and then you have your after. Okay, so what's in the text? Here you go. The transmitted signal still remains upright. That is true. Okay, if you take a look at it, the transmitted signal is still upright. The speed has decreased. That's why V goes down. And lastly, the wavelength. If you take a look at the wavelength in the animation here, let me just run it again. You can see that the before wavelength is much longer and the after wavelength is shorter. And I tried to represent that in the static diagram. Okay, so the transmitted signal will remain upright. That's always true. Its amplitude will decrease by a bit, but the other two consequences is that it slows down and the wavelength shortens. The reflected signal will be inverted. Okay, what if you go the other way around? Okay, I'm going to erase my graphic there down the bottom because I'm running out of space, but hopefully you're going to draw a graphic that's similar to that. Okay, if you need me to just draw along with you for now and then I'll erase it afterwards, yeah, I could do that. Here's my before. It's a more dense medium. I move on to a less dense medium. What is the outcome? Let me just animate that again. And you'll see that the outcome is that when the wave reflects backwards, it reflects backwards still upright. You've lost a bit of amplitude, but it's still still has the same wavelength. Okay? Same wavelength, same speed, in the opposite direction. What about the transmitted signal? Well, here's the crazy thing. Transmitted signal, it moves a whole lot faster and the amplitude has increased. So draw a longer arrow. And here's the visual animation. I don't know how choppy it is back at your house, but if you go into Google Classroom, I've copied and pasted these animations into the classroom assignments. Okay, so on day 6.01, you'll see the pictures over there, and that way you can, I don't know, mesmerize yourself while looking at these animations. They are true to life, and that's why I like them. Okay, so you can see that the transmitted signal, it is upright, the amplitude increases, the speed increases, and the wavelength also increases. And the other side effect is that the reflected signal, it doesn't invert. Reflected signal is upright. All right, so there's a bit more than meets the eye from back in grade 10. Again, in grade 10, you would have learned that the transmitted signal slows down. That's very true. But these are all the other side consequences as well. Unfortunately, I cannot bring the drawing back. I was just drawing it real time. All right, so again, you just draw your before. And then your after. Again, the speed remains the same, just in the opposite direction afterwards. And what happens with the transmitted wave? Well, the transmitted wave will travel with a greater amplitude, greater wavelength, and draw a longer arrow to tell the reader that it travels a lot faster. Okay, so these are inherent properties whenever you change from one medium to the next. There's another famous YouTuber out there, way more popular than the previous guy, and he had a video that talked about ultrasound and how the waves move through different mediums. Okay, so I want you to observe all these crazy, trippy things happening, but this time around in his particular video. Any other questions before I advance onto his video? Yes, what's your question?
So for the first graph, you said it has like a upside down arrow for amplitude and velocity. That means like, what does that mean?
All right, it's up to 2. What does it mean?
Oh wait, never mind. Got it.
Okay. All right. So yeah, Steve Mould. It's pretty cool, this video animation over here. And just to ensure that it plays a lot more smoothly, let me just cast just that screen alone.
So let's say you had to read an incredibly long email from your boss that you had to finish before the
When my wife was pregnant, she had ultrasound scans. That is not my wife, by the way. You can't film inside NHS hospitals, so that is stock footage, which I really like because look at how the image of the baby isn't really changing, and yet this guy's going crazy. Look, woo! Let's look all around the baby. That guy's not a sonographer. Anyway, sometimes I'm accused of not being in the moment, but that's not true. I'm just in a different moment. Like, instead of thinking, wow, I'm seeing my unborn child for the first time, I'm thinking, wow, that machine is amazing. I wonder how it works. And I actually know a little bit about how ultrasound scanning machines work now. What really struck me the last time was the gel that they squeeze onto your belly before they rub the ultrasound wand on it. I remember after the scan, during a moment of contemplative silence, Leanne saying, "What are you thinking about?" And I said, well, I just wonder whether that gel is purely for lubrication or whether it serves some other purpose. So next time we went in, I snuck a look at the bottle the sonographer was dispensing the gel from, and it specifically said ultrasound gel, so it wasn't just a generic lubricant. It turns out that ultrasound gel is specifically formulated to do one job, and that job is acoustic coupling, and it's really interesting, and that's what this video is about. But first of all, what is an ultrasound scan? Well, it's like sonar. So you send out sound waves, they bounce off various things, and you listen out for the reflected waves coming back to you. And you can use the timing to figure out how far away things are. And you can use the direction to figure out where things are. With a sophisticated device like an ultrasound scanner, you can use that information to build up quite a good picture. In the case of a pregnancy scan, it's the baby that the sound waves are bouncing off, specifically the baby's bones. The purpose of the gel is to sonically merge the probe and the human body into a single acoustic entity. And by doing so, it removes unwanted reflections. Think about this. If you stand in front of a wall and scream, like I do for relaxation, you'll hear your scream coming back at you because walls reflect sound. But sound also passes through walls, like this aeroplane. My studio is near City Airport in London, which is annoying. So the question is, how much acoustic energy gets reflected and how much gets transmitted at the interface between two different substances? And why? That's what we need to figure out. And to do that, I've got an analogous wave system. So sound waves are longitudinal, which means the vibrations go in the same direction as the wave is traveling. These waves are transverse, so the oscillations are perpendicular to the direction of wave travel, but the physics is the same. So look, if I lock one of these rods in position, then this is going to be like a sound wave coming up against a really solid, unmovable wall. And you can see that the wave gets reflected completely. And you can see why. If you look at the rod that's just next to it, as the wave comes in, that rod is pulled upwards. That creates tension in these two cords here, which pulls the rod back down again. But it actually travels past the origin and goes much lower than it. And that pulls on the rod next to it, which pulls on the rod next to it. And so the wave travels back in the direction it came from. Sound waves don't reflect completely off of walls because walls have a little bit of give, and we can simulate that by adding weights to the wave machine. So the heavier rods represent the wall because, like the atoms in the wall, they're harder to get moving. In this case, because of inertia. Look what happens when we send an impulse up to the boundary. It's partially reflected and it's partially transmitted. Notice, by the way, that the transmitted wave is traveling slower than the incoming wave. That's not true for sound going from air to wall. Sound actually travels more quickly through the wall. That's because this analogy isn't perfect. If I add even more weights, then even more of the wave is reflected and less is transmitted, which makes sense because we're getting closer to the situation where I was physically holding one of the rods in place. So hopefully you can see that the more different two substances are, the more reflection you get and the less transmission you get. When I say more different, I'm actually talking about something called acoustic impedance, which is a measure of how much does a substance resist acoustic motion, basically the vibration of atoms and molecules that is sound. It's a bit like refractive index when you're dealing with electromagnetic waves, if you're familiar with that. The only difference is that refractive index is the inverse of wave impedance. The human body has an acoustic impedance of about 3,000 times that of air. So if you want to work out how much sound that is produced outside the human body ends up inside the human body when it passes through the boundary between the two, you put the two acoustic impedances into this equation and you get out an answer of about 0.1%. So hardly any. And by the way, you get the same problem in reverse. If you go from high acoustic impedance to low acoustic impedance, you get reflection as well. Hopefully you can see that we would expect that intuitively if I show you what happens when you go from some impedance to zero impedance. You see, if I pinch these two chords together, the cord is providing no torque to resist the twisting of that final rod. This final rod actually travels higher than it would normally because it's unimpeded on this side. And so that pulls on the rod next to it, and that pulls on the rod next to it. And so you end up with a wave traveling backwards, a reflected wave. So without ultrasound gel, 0.1% of the acoustic energy would find its way into your body, and then 0.1% of that would make its way back out again for the receiver to pick up. 0.1% of 0.1% is 1/10,000th of a percent, completely useless. What ultrasound gel does is remove the boundary between different acoustic impedances. It removes the impedance mismatch. It's formulated to have the same acoustic impedance as the human body so that there's no barrier between the speaker and the inside of the human body and the inside of the human body and the microphone inside the probe. I don't know if speaker and microphone are the right words in this context, but at least you know what I mean. While we're on the subject of ultrasound scans, I want to tell you about a collaboration between art and science that I think is really interesting. It's called Ode to the Future, and it's a collaboration between
I guess for more adventures than that, you can keep on watching with Steve Moult and all his fun-filled antics. Would that mean that the baby could hear the people talking outside? Yeah, the baby can. The baby really can. It'll just sound like mush, that's all. I mean, place your ear against somebody else's ear that is okay with you putting your ear against their ear and just listen through what the sounds through there, right? It's going to be muffled out simply because the flesh absorbs high frequencies really well. All right, so really only the lower end frequencies pass through, and that's why it sounds all muffled up. Isn't the whole thing that babies will kick in response to certain sounds? Possibly, but let's save that for biology. Okay, let's save that for biology class. I know there's a lot of cool things over there. Yeah. Okay, so the point of the video is I hope that you were able to see these animations happen in it in real time. All right, with regards to his crazy contraption that he made. Hopefully one day I'll find the time to build it as well. I'm sure that took him a good 2 afternoons or more to build up that, plus buying all and sourcing all that hardware. Okay, but this is the reality of whenever you change from one medium to the next. One last thing I want to talk about before we move on to our calculation question here is take a look at the frequency of this setup. Okay, I'm only transmitting one wave at a time. On the far end, I'm only receiving one wave. Yeah, it's taking me longer to hear it because it's traveling through a slower material, but eventually it gets to its destination. What I want to get at is that anytime you transmit from one medium to the next, you never change the frequency. All right, so before and afterwards, frequency remains the same. Oh, my handwriting's terrible. Frequency remains the same. All right, so you may want to have that in your notes as well. Okay, so knowing that the frequency remains the same, but what does change is the wavelength, let's go and solve the next problem. Okay, so taking a look at this question over here, without looking at the number specifically, you notice that it's traveling slower through air and faster through steel. In other words, air will behave as the more dense medium, all right? And the steel will be the less dense medium. So it's going to travel a lot faster, and it's going to have a longer wavelength and a greater amplitude. That will be the outcome. All right, so the incident wave will travel this way at first, but the reflection will be of the same speed, just a lower amplitude. The transmitted wave will have a longer wavelength, higher amplitude, and what else? Faster speed, yeah. Higher amplitude, faster speed, longer amplitude. Okay, so we'd expect to have an answer that is bigger for a new wavelength through the steel. Okay, so how would we calculate this out? As I mentioned, the frequency will remain the same. So the frequency does not change when you go from one medium to the next. Okay, I'll start off with our givens, and then we'll work from there. So what are our givens? We know that the wavelength in air is equal to 0.750 meters. The speed of sound through air is roughly at 345 meters per second. Now we're given the speed through the new material. I'll just call it S. I was about to write down B, but we'll just call it S for steel. All right, which is at 5050 meters per second. So it's well over 10 times faster. Okay, so we should see a significant change. And again, according to the predictions, the wavelength should be a lot longer. Okay, and we're trying to find out what is a wavelength through the steel. Remember that frequency remains the same. So the frequency through the first medium of air is going to be equal to the frequency through the second medium, which is through steel. Okay, we're going back to the example about, what do babies hear? All right, again, if you want to simulate yourself as a baby, go to one of your siblings or your parents and just snuggle with them, place your ear beside their tummy, and have the TV playing in the background, right? And as you carefully listen to the sounds of the TV through that flesh, again, you're going to lose out on the higher end frequencies just because the body absorbs higher end frequencies. But what you hear afterwards, the muffle, well, that muffle is the original recording, and it does not pitch up or pitch down. Okay, so it's not like you put your ear against somebody's stomach, and then somebody talking in the other room, suddenly they start sounding like Mickey Mouse, all right, or baritone voice. All right, I can't remember the artist's name. Okay, so no, your pitch doesn't change. The frequency still remains the same. Okay, so frequency through the air is the same as the frequency through the steel. So how do we solve this problem here? I think some people, what they'll do is they'll use the universal wave equation, V equals F lambda, solve for the frequency, and sub it into the next equation. That will work out. That's fine. All right. But here's what I want to introduce to you, the whole idea about comparing before and after. So anytime that you're solving problems where you're looking at before and after, you only have one formula, you can either solve by substitution, elimination, or you could solve by division. And that's the step we're going to take. What we're going to do is we're going to take the formula, V equals F lambda, and we're going to divide the formula by itself. I kid you not. We're going to take the formula, and we're going to divide it by itself. Okay, you could call it 2, 2, 2, 1, 1, 1 if you want to. In this case here, I'm just going to use the letters A and S. Okay, so I'll just have, I don't know, I'll just use steel on top, and I'll have air down below. One thing I did mention to you is that the frequency through air is the same as the frequency through steel, so those two divide each other out. What we're effectively doing is creating a brand new formula. So the relationship between the speed of sound through steel and air will be also equal to the ratio of the differences between the wavelength of steel versus the wavelength of air. Quickly rearranging for lambda S, since that's what we're solving for, that's equal to lambda A times Vs over Va. Okay, so lambda A is equal to 0.750 meters times this ratio relationship. Again, according to the diagram, I'm predicting that the new wavelength will be quite a bit larger, probably more than 10 times larger. I'm assuming around 12 times. Divided by 3, 4, 5, and you get, yeah, almost 11 meters. How many sig fig is this problem? Looks like 3 sig fig, so I guess 11.0. Okay, my calculator gives, yes, 10, 8, or 978. Got 1 more minute before the break, so 10.978 meters. They'll just round to 11.0 meters. Okay, and that is it for this lesson for this time block. How do you do the equations equal to each other? All I did was I took the equation and I divided it by itself. So I took the equation and I divided by itself. That's all I did. It's a method that you can do to compare before and after, and we will be using that technique in solving a lot of problems in this unit as well as in our last unit. Why is f of a equal f of s? Again, when you take a look at the animations, let me just erase everything here because everything here has already been stated as a PowerPoint recording. So there you go. It's already been recorded. Again, when you take a look at the animation over here, if I'm transmitting at 1 hertz, on the far side, I still only hear it at 1 hertz. So the frequency doesn't change when you go from one medium to the next. The only thing that does change is the wavelength, the amplitude, and the speed. Those 3 factors change, but the frequency won't change. All right, so I'll leave you guys with that. Again, the homework for this part is course pack 63, questions 1 through 8. Yeah, read up on the lab. You don't need to read and research, just read, that's it. Okay, so I'll leave it with that.